Alright, so today we're going to talk about the Euler Lagrange equation and how to derive it. So in a lot of situations in math and physics, we need to minimize integrals that take this form, where x is going to be the independent variable and y is going to be the dependent variable. So for an example of where we'd want to minimize this would be the arc length in the plane. So from calculus, we know that this integral right here will give us the arc length. So if you want to minimize this between 2 points x1 and x2, then we need to minimize this integral. So in other words, f of x, y, and y dot would be this right here. And this f is going to be dependent on the situation. So if we want to minimize the arc length, then we're going to have to minimize this functional right here. If we want to minimize something else, so for example in physics, we want to minimize something called the action, which we'll get into in the next video, then we'll have to minimize whatever that function is. So to do this, we're going to use another theorem from the calculus of variations, not the one that we did last video, but it's pretty similar in how it's proved, so we won't prove it here. But it says that if a functional is going to be at a minimum, then its first variation must be 0. So if you looked at all the different ways that you could construct a path through space, so in our arc length example, maybe the length of this line is 1, then we need to look at all the surrounding points, all these surrounding functions, and if a tiny change in our function results in a 0 change in the output of the functional, then it's going to be at a minimum. Now, this is a necessary condition, but it's not usually sufficient. So what does that mean? That means if a function is at a minimum, then its variation is equal to 0. However, if the variation is equal to 0, that does not imply that we have a minimum. So kind of like how in Cal 1, if we wanted to minimize a function, we would take its first derivative and find the critical points. We would need the second derivative to figure out if something was actually a minimum or a maximum. So we have a similar problem in the calculus of variations, but luckily you can usually tell on physical grounds, or maybe we don't really need a minimum. So that'll come into play next video whenever we talk about minimizing the action. We actually don't need the minimum path, so we won't have to worry about that complication. And like in this example with the arc length, it makes sense that if this was the solution to this minimal integral problem, that it's going to be a minimum, because we could construct any arbitrary curve that has those same endpoints, and these would have infinite length. So it's pretty clear that this path is the minimum. Alright, so now we get to the fun part, actually deriving the Euler Lagrange equation. So we want to minimize the integral right here. And what we're going to do is suppose that we have some correct solution, y of x, and then alter it by some function. So if we want to take that arc length example, we would suppose that we had some correct path. We don't know exactly what it is yet, but then we're going to alter it by some function eta of x. So this would be y plus alpha eta of x. What's alpha? It's going to basically scale this function. So this could be for a different alpha, this for a different alpha, and we're going to basically alter our path by scaling some arbitrary function. And the restriction that we're going to put on eta of x, so that this makes sense, is that it disappears at the endpoints x1 and x2. Otherwise, it wouldn't make much sense. Like in this ArtLink example, if we allowed paths that look like this, well, that's not going to make any sense because they need to pass between these 2 points. So, we then have this function for y of x, because we're perturbing it by some amount alpha eta of x. So we have y of x alpha is equal to y of x plus alpha eta of x. And then just because we're going to need this a little bit, if you compute its derivative with respect to x, you just differentiate each part. And then I should mention that alpha is going to be a scalar that's just going to scale that eta of x, that arbitrary function. So whenever we differentiate this term, it's just eta dot of x. So now we want to see how this functional is going to change with alpha. So this di over d alpha, once we're done, should be equal, we're looking for functions where di over d alpha is 0. So if we just differentiate this integral, we're gonna pretty quickly run into a problem. Because this isn't like Cal 1, where you would just differentiate some function. Right here you're differentiating an integral, which is a different beast. So luckily, there's a theorem in calculus that allows you to bring this inside the integral sign as long as it becomes a partial derivative. And there can be complications where if this and this are functions of x, then you have other terms, but that's not the case here. So we can just directly bring this partial derivative, well, this derivative, inside and make it a partial derivative. So from multivariable calculus, we know that if we want to differentiate this function f, we need to differentiate it with respect to each of its variables. So we have, well, first off, we have partial f over partial x, and then partial x over partial alpha, but x is not a function of alpha, so that term just becomes 0. So the only two terms you're left with is partial f over partial y, and then chain rule tells you partial y over partial alpha. And then similarly, for y prime, you have partial f over partial y prime, and then chain rule tells you partial y prime over partial alpha. Now, this doesn't look very pretty at all, but if we look at our definitions from earlier, then partial y over partial alpha is just going to be equal to, well, this right here is not a function of alpha, so it just goes to 0. And this right here, if we're differentiating with respect to alpha, and alpha is a scalar, alpha becomes 1, and eta of x is treated like a constant. So then, this term right here is just eta of x. And by a similar argument, right here, partial y prime over partial alpha is going to be eta prime. So then, if you substitute those in, you get this. Now, this looks a little bit prettier, not much, but here we kind of see where we're trying to go. So, if you remember from last video, if you have an arbitrary function that vanishes at the endpoints, if it's multiplied by some other function, then that function has to be, the function that you multiply it with has to be 0. So we want to figure out a way so that we can multiply eta of x by all of this. But here's the problem. We have eta prime right here. So we need to figure out a way to basically, we want to integrate that part. So that probably seemed a little bit suggestive because we want to integrate this term by parts. So if we integrate this term by parts, then we're going to choose this to be dv, because we want to integrate this part, and this part to be u. So if you substitute that into the integration by parts formula, it says it'll be u times v, so the integral of this, which is just eta of x, minus the integral from x1 to x2 of du, so d over dx of partial f, oh, this is supposed to be an f right here, my bad, of partial f over partial y prime times eta of x, because it'll be times v dx. Now, this looks like we may have made the problem worse, but we haven't, because eta of x is supposed to vanish or be 0 at x1 and x2. So this term right here is just going to be 0. So I promise we're getting to the end. If we plug all this in, so we keep that first term the same, and then we plug in that minus d over dx, partial f over partial y prime eta of x dx, then we can factor out that eta of x since each of these is multiplied by eta of x. And then we get this term on the inside. And then by the fundamental lemma that we discussed in the last video, if this is arbitrary, then this has to be 0 for all x1 to x2. So then we get the Euler Lagrange equation. And this is going to be a very important equation because it's going to be the foundation of Lagrangian mechanics, which we'll start to get into in the next video. So if you enjoyed this video, just let me know in the comments. Let me know if you have any questions. See you in the next video.